In our first round of videos about the volumes of solids of revolution, when we used the disk method, we were always revolving around one of the axes, either the x-axis or the y-axis. So, if you recall, let's say we had a function like y equals x squared, and let's say we were looking at it, above the x-axis between 0 and, let's say x equals 3. If you were asked to take this and revolve it around the x-axis, you recall the first step was determine what the thickness is. Well, because we're revolving around the x-axis, our thickness was dx. Our second step was to find out what the radius is. And I gave an instruction in that may not have stood out because it was in the middle of so many others, but this step right here is going to be key for what we're doing today. To draw the radius, you start at the axis of rotation and draw perpendicular until you get to the function that you're looking at, right? That distance is what the radius is. Now, in the previous lessons, that was always just the function. It was, well, because this is dx, our radius will be the function expressed as x. So my radius for this problem will be x squared. Right? The third step was for us to find the bounds. In this case, it's between 0 and 3. And the fourth step was to write the integral. We say, all right, well, it's pi times the integral from 0 to 3 of radius squared times thickness. And that was the end of it, right? Today's lesson is about what happens when we take one of these regions, and we're still using the disk method, but we're revolving around some other axis. And I'm just going to give a brief taste of that now, and then we'll get into the three examples that I have. Suppose, for instance, that you had a function, or you had a region that was, something like this. And, so we're talking about this region here. And let's say I want to revolve it around this line up here. Let's say this is x equals 4, right? When I revolve that around, we can even talk about it. Step 1, would it be dx or dy? And the answer is, because you're revolving around something horizontal like the x-axis, it's still going to be dx. The second step is where things get interesting. And all I'm going to talk about now is how we draw it. We'll get to a specific example in the next slides. Think about what I said about the radius earlier. I said that to draw the radius, you draw from the axis of rotation up or down until you get to the function. And that distance right there, that is your radius, right? And previously this was always like, it's just the function. In this case, what I really want you to see this as is I want you to see that this is basically the difference of two things. This is always going to be, whatever the top thing is minus whatever the bottom thing is. So in my example here, we could say that distance is x, which was the top thing, minus, and I'm just going to sort of fake it and say f of x, because we could say that this curve that we were talking about here, we might have called that f of x. And so that expression is what you're going to use as your radius and what you'll use through the rest of the problem. So that, like the four steps that we learned yesterday, these aren't changing. What's changing today, what's being affected today, is that because we're not revolving just around the x-axis, because we're revolving around something else, we're going to need to work a little bit harder to figure out what that radius is. So like I said, I've got three examples, so we're going to jump into those right now. Alright, so the first one, and this is, the structure I'm using here is a fairly common structure for the question for the AP exam, so you might want to get used to that. So we let R be the region bounded by this thing. As soon as I see that, I start drawing it, right? So I hope we all know what x cubed looks like. It looks, roughly like this. Here's x cubed. Right, y equals 8, that means there's a, horizontal line up here, y equals 8. 8, and the y-axis, so that's this guy here. Alright, so the region bounded by that is basically all this region here. Okay, so I want to write an integral expression for the volume of the solid generated when this region R is revolved around the line y equals 8. Right? I just realized I had a mistake on that other page. I think I had said it was x equals 4, and that should have been y equals 4. Oh well. So let's work through this, right? Step 1 is the same as we said yesterday. We figure out what the thickness is. Right? And I mentioned in the previous slide, the thickness, because this is y equals 8, it's horizontal just like the x-axis. the thickness of this thing is going to be dx. Because I'm revolving around something horizontal like the x-axis, it's dx. Second step is radius. And this is the one that I said was going to take us a little bit of effort, right? I said that to draw the radius, you need to start at the axis of revolution and go toward the function, go perpendicular down to the function. And then what we do is we do a quick little top minus bottom subtraction. So in this case, the top function is the function y equals 8. So the top is 8 minus. The bottom is this function here, y equals x cubed. So x cubed is that bottom function, right? And so just to sort of solidify that in your minds, 8 is basically this whole distance, x cubed is this distance, so the distance in between them should be 8 minus x cubed. So long story short, our radius is 8 minus x cubed. Step 3 are the bounds. Because this is in terms of x, I'm looking at the x-axis. I basically need to figure out where does this start and where does it end. Well, we can tell it starts here at 0. Where it ends over here basically depends on what, if you sort of follow it up, depends what this point of intersection is. So what we're looking at is where is this line equal to this function? Where is 8 equal to x cubed? Clearly the answer is x equals 2, so my bounds are going to be from 0 over to 2. Right? And then finally our fourth step is to actually set up the integral. And remember that the setup for the integral is the same for all of these disk method problems. It's the integral of pi r squared times whatever the thickness is. So in our case, we pull out the pi because it's a constant. The integral from 0 to 2 of 8 minus x cubed, that was the radius, squared, times the thickness, which was dx. And that's actually the end of the problem. That's the answer that I was requesting. You may ask, oh, could we compute that? Sure we could. But this question was asking for an integral expression for the volume. In other words, they just wanted you to give the integral form of the answer. This is a very common way of asking a question on a non-calculator section, because it means you don't have to go through all of the computation. I'm going to go to my second example. So another fairly similar one. In fact, I might recommend that you even try this one on your own because it's very similar to the last one. The third example is quite different. So if you want to try one on your own, or if you're short on time and you want to skip one, I suppose this would be the one to do. But try it out on your own. So let's see here. First thing we do is we draw the region. So first of all, 6 over x. 6 over x is like the 1 over x graph, but it's taller. So you sort of got something like this going on. So you've got that, you've got y equals 2. Let's see here, y equals 2 is a line, it's a line here. X equals 1 is a line here. And so the region we're looking at, so this is 1, this is 2, the region we're looking at is all of this inside here. And they want an integral expression for the volume of the solid rate generated when S is revolved around the line y equals 2, so revolved around this line. So again, I'm going to recommend you pause the video if you haven't done so already. Remember what the 4 steps are, work the 4 steps out, and then check your answer. So first step, is it dx or dy? Well, I'm revolving around a horizontal line like the x-axis, so it's dx. Second step, I'm supposed to draw from the axis of rotation or revolution up to the function. I'm supposed to reflect on what that distance is. And I mentioned previously it's the top function minus the bottom function. My top function was 6 over x minus my bottom function was 2. Great, so my radius is 6 over x minus 2. As far as the bounds of integration are concerned, I'm doing this in terms of x, so I'm looking on the x-axis. I clearly start here at 1, and I end wherever that is. And note that that value is caused by the intersection of the y equals 2 function and the y equals 6 over x function. So I'll set those two things equal to one another. 2 equals 6 over x. That means x equals 3. Great. So my bounds of integration are from 1 to 3. I'm a little bit short on space here for step 4, so I'll move it here. This is going to be pi times the integral from 1 to 3 of my radius, 6 over x minus 2 squared dx. And that is our integral expression for the volume. I've got one more of these. Finally, let T be the region bounded by, and I apologize for this. This was the only notation I could use here. It should be clear. What this just means is it means the square root of x minus 2. Okay. So let T be the region bounded by that, x equals 2 and y equals 4. So again, I'd recommend you try and draw this on your own before I do it. That's your cue to pause. X minus 2 means it's been shifted to the right by 2, so you've got a square root graph. X equals 2 is this line. And y equals 4 is this line here. So this is 4, this is 2, this is our x-axis, this is our y-axis. So let's see here. They want an integral expression for the volume of the solid generated when this region is revolved around the line x equals 2. So when we revolve around this line. Right? Okay, so this is where things are going to get a little bit different, right? Step 1 is the same step. Is this a dx or a dy problem? So you should pause and consider that. Because I'm revolving around something vertical, like the y-axis, this should be dy. Second step, and this is really the one where we need to pay attention. I need the radius of this revolution. I mentioned in both of the previous problems that to do this, I'm supposed to draw from the axis of revolution perpendicular to the other function. I need to know what that distance is. And what I mentioned in the previous ones was that you're supposed to do the top function minus the bottom function. There isn't really a top and a bottom here because this is side to side. So your option is either turn your head sideways or, turn your head sideways and realize, oh, this one is on top, this one is on the bottom, with respect to the y-axis being 0. Your other option is that when it's done sideways, when you look at this thing, just look at it as right minus left. Okay. The other catch here is that because I'm doing this problem sideways, I have to take this function and rewrite it. And one way of thinking about that is, note, what is the left function? The left function here is x equals 2. My right function, this one here, is y equals the square root of x minus 2. I hope you, and you might want to take a second to understand this. I can't subtract these two things because this is, pardon the old adage, this is apples and oranges. I can't subtract a y and an x value because they're not even the same. I need to change this y value into an x value. I need to say, oh, y squared is x minus 2, add the 2 over, y squared plus 2 equals x. And now I can say, my right function was x equals y squared plus 2. My left function was x equals 2. And so the distance between them is the right function minus the left function, which actually very conveniently ends up showing us that y squared is the radius. Okay, we're almost done. Step 3 is where we're supposed to figure out what the bounds are. Right. So the bounds, because I'm doing this in terms of y, my bounds are y values. I'm starting here, I'm going up to whatever this is. So we can definitely tell this started down here at 0, and it goes all the way until we get up here at 4. So this is easy. We can tell the bounds are from 0 to 4. And so the last step for us is to just write out the integral expression. And because this is the disk method, it's actually the same thing. This is pi times the integral from 0 to 4 of my radius, which we determined was y squared. And recall that y squared came from the right function minus the left function. And then dy. And that's the end of this one. This is a fairly long lesson. The other two that I'm going to be doing today are shorter. I had a lot that I needed to get through in this one. So hopefully those made sense, and good luck in the next one.